Hey guys, Lego Masa 99 again with another video today, and today we are back in the Redstone Computer version 4.0 world here, as you guys can probably see. A lot of you guys have seen this, but yeah, I am back in this world today, and you might be asking why. And the reason is that I am going to be doing a video breaking down and explaining how this big mess and contraption of Redstone actually works, how it operates and everything, just like I did with the Redstone Computer 3.0 video that I did previously. So yeah, without further ado, let's get started. Alright, so the Redstone Computer 4.0 shares a lot of similarities with the Redstone Computer 3.0, but also has a lot of differences and that sort of thing. And this video will be structured in a similar way compared to the Redstone Computer 3.0 breakdown video that I did. And if you guys haven't seen that yet, I would recommend you guys going to check that out because I explain a lot of the fundamental concepts and how the general computer model works that I use. And I'll be explaining that briefly in this video as well, but the Redstone Computer 3.0 video covers a lot of that stuff as well. So just like in the 3.0 breakdown video, we will first start off with explaining everything on this UI panel and how it all works and all that stuff. Alright, so first we're going to start off with the computer power controls, and these three are also present in the Redstone Computer 4.0, and they basically function the same as the Redstone Computer 3.0. The on button essentially initializes the computer, prepares it for code execution, and then it also allows the clock pulse signal to propagate down to the cores that are enabled, which I will talk about in a second. And the core clock runs down this wire, I'm pretty sure, right here, and then it gets distributed to the different cores to initialize them. And when you sleep the computer, that basically just disables the pulse from updating the cores. And then when you turn off the computer, it resets all of the registers, it turns off the computer officially, and then it also runs these settings here, which I will explain in a second. For the software speed control here, or just the speed control in general, it works similarly to the Redstone Computer 3.0, except that instead of levers, we have sort of a button system here. And I demoed this in my Redstone Computer 4.0 video, so I'm not going to show it to you here. You can go check that out if you haven't seen it yet. And also in this computer, this instruction set, which I will go into more depth later, that this computer has supports software speed control, where the Redstone Computer 3.0 does not support that. And to enable that functionality, you need to flip the switch, and basically what that will do is that it will start the computer or start the cores with the speed that you have selected here, but you no longer have control over changing that unless you turn the computer off and then you flip the switch off and then you change the speed. So once you flip the speed, it hands over all speed control to the instruction set and the program itself. And to change the speed, you'll have to do it through there. Alright, so the core enabling panel here, this is pretty self-explanatory. These are just T flip-flops, and you just push the buttons to enable or disable the cores. And also we have the RNG toggle here. And this works in the same way that the Redstone Computer 3.0's random number generator worked. Let's see here. Let's follow this wire down here. Essentially, what it does is that if we run all the way down here, as you can see, when we turn the random number generator on, it starts basically giving out random pulses, and whenever the computer requests a random number generator signal or a number from the random number generator, these pistons will extend, enabling these signals to propagate through the master output bus, which I will explain in a second, but that is also covered in the Redstone Computer 3.0 video. I know I'm referencing the other video a lot, and that's because there are a lot of similarities that both of these computers had, like I mentioned earlier. So here we have the computer input panel, and this works a bit differently compared to the Redstone Computer 3.0. In that computer you had levers, and in this computer here, it is more of a memory system. So you push one of the buttons to toggle it, but you can't untoggle it. And the inputs essentially turn off when the computer requests any sort of computer input signal. So if a program asks if computer input 1 is toggled, it'll reset after that check is done, regardless of if it's on or not. And then to reset that, you can just press the off button like that. And while we're on that topic of user input, here is our other user input panel, and these are also just T flip-flops. And then this connects back to the computer so that you can send user input into the program, which is essential. All right, so on this side we have our 4 computer indicators. So these are indicators that are controlled by the program, and we also have our shift overflow and shift underflow lamps here. And basically the shift overflow light will turn on when one of the ALUs, or arithmetic logic units, does a computation that exceeds the 8-bit limit, which is 255. And then the shift underflow light will turn on when the ALU does a calculation that makes the answer go below 0. Since both of those cases, this computer cannot really support that. Over here is the, I guess, peripheral control panel. It's not really the official name for it, but these are just some options to clear stuff and reset things. And as you can see here, we have the reset RAM on shutdown and the reset displays on shutdown. Now, displays includes everything on this big iron panel here, I guess. So the screen, the decimal display, and the raw binary display as well. And then also we have here the clear decimal display register, the clear raw binary display register, and then clear the display. So if you just want to clear like a component of this instead of clearing the entire thing when the computer is turned off, you can do that by pressing one of these buttons here, and you can do that manually. And so that just about covers all of the buttons and stuff down here. But if we move up here, we have the core, I guess, line of code instruction info panels here. And essentially what these are is that it indicates or tells the user what line of code each core is currently on if it is enabled. So if we go ahead and we have our checkerboard program turned on here. I'm going to turn that off because it might be lagging. Now if we turn the computer on and core 1 is enabled, this will update with the line of code. So as you can see, we have line 1 of code, and then this should update to line 2. There we go, line 2, and then line 3. So this basically gives the user a visual on what line of code the computer is on without running down to the core itself and checking. And there we go. And the computer turns off, and that was the checkerboard program, which is demoed in the Redstone Computer 4.0 showcase video. Alright, so now that we have gotten the user input panel here out of the way on how that all works and everything, we are now going to move into the breakdown of the data flow in this computer and how that works. And I might sound like a broken record at this point, but it is similar to the Redstone Computer 3.0 fundamentally. So let's go ahead and take a look. So we'll go ahead and go down to core 1, which I'm pretty sure this is core 1 right here. And the data flow starts with the program memory here. And essentially what happens is that when the computer turns on, the first line of code gets loaded into the program memory registers, which is this really long green portion here. And essentially what happens is that the each instruction, or what the each, I guess, line of code, if you will, that the computer has to execute will be loaded through here. And once it is saved into these registers, it moves on and gets decoded, since all of the information for each instruction is encoded, or else it would be essentially impossible to have every single option in here. It would be way too impractical. But everything here gets decoded, and then let's see here, and I will break down that in a second. And then once that happens, the data and the opcode, the operation code for the instruction, is sent to the ALU. So the opcode, which I'm going to call it, is decoded in this decoder right here, and that signal is sent to the core's ALU, which is let me see here, everything in orange right here for each core. So this is for core 1, and then for core 2, and for core 3, and for core 4. And these ALUs support the same operations for the ALU that the Redstone Computer 3.0 does. So we have add, subtract, not, this is inverting, and then bit shift left and bit shift right. And once that is computed, or once the instruction is finished, the output will be pushed onto what is called the master output bus, which is right here. It's this gray bus. And this runs down the entire computer all the way through here. And essentially all of the outputs are pushed onto this bus from every single peripheral component, even the ALUs and everything, all merge into this bus. So we have our random number generator here. We have the outputs from each of the cores that are on here. We have all sorts of things. And where this ultimately ends up is, if we follow it down here, it goes all the way down to the memory. So this is the RAM here. This has 31 bytes of dual read memory compared to 15, I am pretty sure, of the Redstone Computer 3.0. And yeah, so once that output goes to the RAM, it is usually saved here. And then in the next instruction, more data is usually read from this RAM here. And since I mentioned this is dual read memory, we have our read A up here and our read B. So if you wanted to add two numbers, you would load up number 1 here and then number 2 there. And then let's see here. Yeah, so those inputs, or those numbers, I guess, then travel around back up to the ALUs again to be input. So it's basically a big loop that goes from the RAM to the ALU to the master output bus and then back down to the RAM again. And that is all controlled, and how that data moves and everything and how to manipulate that data is controlled by the instruction set, which is right here, which is all of this stuff that gets decoded each time the computer pulses a signal. And I will break this down really quickly here. So this component here is the go-to, I guess, go-to section. So basically, each line of code has the next line of code programmed into it, or a condition to determine which line of code to go to. And just the lines of code to go to next are stored here. So if a condition is true, or if a condition is true, it's in one of these, and then if it's false, if it's in another one. Excuse me, I can't really talk that much. I haven't recorded in a while. And then this gets sent to a decoder here, which basically reads that specific line of code. And then we have the condition decoder here. So let's say you wanted to jump to a certain line of code. If a certain condition was true, you would put that condition here. And there are a bunch of different conditions which are all listed in these signs here. And I will just go through all of them. So some of them are, at least most of them actually are arithmetic conditions that are from the ALU, and then the last 4 here we have the computer inputs, and then we have if the random number generator is on or not. And then we have the this is what's called the immediate input in the instruction set, and essentially this is where you can send data through the program straight to the ALU. So if you took a number that was stored in RAM and you wanted to add like 5 to it, then you would put that 5, that constant, in here to do that. And then we have the RAM control here. So this is essentially what addresses, so what essentially spaces in memory to read and write from, which is put here. And then we have our opcode, operation code for the instruction. So this basically tells the computer, what do you want to do in this instruction? So we have add, subtract, not, all of the ALU operations, and we have some IO stuff. And new with the Redstone Computer 4.0 is GPU stuff, or GPU opcodes rather. So we have GPU reset, GPU draw point, GPU erase point, GPU granular, and I will get into all of those later when we talk about the GPU on the screen. I should rather just call it a plotter because there's no real graphics processing here, but that's what it's referred to in the instruction set. And then here we have some, these are just options. This is just to essentially select options for certain opcodes. So for an example, if we had the IO output instruction, you would put, or in here you would encode what specific device or peripheral to output to. So if you wanted to output to the decimal display up there, you would first of all select IO output as your opcode, and then you would specify that you want the decimal display by putting that its correct value in here. And this is the cache control. As I mentioned in the Redstone Computer 4.0 video, this computer has a caching system for extra memory and faster memory, and I will talk about that later as well. And then over here we have more caching stuff. It's just this is for caching the specific addresses that you want to use and that sort of thing. So that is essentially a breakdown of the data flow in the computer and a little bit of a breakdown of the instruction set here for the Redstone Computer 4.0. Alright, so now that I have explained the data flow, I'm going to go ahead and break down how each one of these cores is wired and how it works. And each one of the 4 cores is essentially identical in functionality and everything. So let's go ahead and start at the input of the core. So just like the Redstone Computer 3.0, there's an input A and an input B, and the signals from, or the data from RAM that I was talking about earlier, when you read data from RAM, it travels up these buses and it stops essentially right here. And as you can see, it won't travel forward unless these pistons are retracted, which happens whenever we have any ALU opcode selected. And once the data is allowed to go flow through into the ALU, it goes through the ALU, I guess, master bus. I think that's what I called it in the Redstone Computer 3.0 video. It's essentially the same concept. The data runs through the entirety of the ALU, and in this case it's more compact. So it runs all the way through here, and then it branches off into different components of the ALU to manipulate that data on. So on the left here we have the ALU, or not the ALU, excuse me, the adder and the subtractor. What is it? In this iteration of the Redstone Computer, the two's complement that is necessary to do subtraction is integrated into this ALU, or I keep saying ALU, adder, sorry. And this is also proper English's, I'm gonna say it's English, yeah. Proper English's adder here. Big props to him, because in my opinion, this is one of the best adders out there. And so that is the adder and the subtractor. And then on, let's see here, we have the NOT opcode to invert the signals right here. It just branches off and goes up here. We have the bit shifting left and right, I guess, circuit on this side, on the left here. And then we have the binary comparator at the very end, which essentially compares the two inputs and sees which one is greater, which one is smaller, or if they're equal, and that sort of thing. Oh yeah, with the binary comparator as well, all of the signals that are sent here, essentially the A equals 0, B equals 0, the greater than or less than, and the equals to, all of that is sent to the ALU conditional register, which is right here. And essentially every instruction, this will update with the correct status of the numbers that are being manipulated. So if I wanted to add 5 and 7, this register would update while that calculation is being performed. This register would update with the fact that 7 is greater than 5, and that A is not equal to 0, B is not equal to 0. There is no shift overflow, there's no shift overflow and all that sort of stuff. So all of those flags essentially are stored here, and then the outputs of that essentially converge in the conditional decoder, or the conditional section of the instruction set, which I discussed a few minutes ago, and that essentially determines whether the condition is true or not. So if we wanted to test for a shift overflow, we would need to, this is basically an AND gate here, and both of these need to be turned off for this line to turn on, which essentially means that the condition is true. And for both of these to turn off, you need to be testing for the condition, and the condition needs to be true, and this condition true data comes from this ALU conditional register, as well as for the computer inputs themselves. And then this just connects back up to the user input panel. Oh, also, oops, I forgot one more. We have the GPU point encoder here. I will explain this when we talk about the GPU and the screen, but that is also here. And all of those, the results from all of those calculations merge onto this gray bus that you see here. I guess this is the ALU output bus. And this all merges to the ALU output register, which is right here. And essentially what happens is that when the data is let through, it essentially computes through all devices at the same time. And what happens is that based on the opcode that you've selected in the instruction set, it will choose which output to use from the peripheral, if that made any sense. So all the data would basically be added, it would be bit shifted, it would be inverted, it would be compared against, it would be encoded and everything. It would do all of that at the same time. And then let's say we wanted to do a bit shift left, it would select the bit shift left output from the bit shifting circuit to push onto the output bus here, and then that output would be saved to this register, and then once it is saved there, that output is pushed back onto the master output bus, which runs right here, and as I explained a few minutes ago, it'll run all the way down back into memory. So that is essentially how the ALU works for each core here. But with the Redstone Computer 4.0, there is an extra component to each ALU that was not present in the Redstone Computer 3.0, and that is the inclusion of a cache. Alright, yeah, so the Redstone Computer 4.0 has a cache on it, and I'm pretty sure it is, I think it's 4 bytes of read-write memory. Yes, of dual read, dual write memory. So that is right here. And let me give you a perspective of where the cache is. So let's go out here. So this is the ALU right here, this orange part here, and then the gray and the orange up here is the cache. So the cache essentially sits right on top of the ALU, and the cache is deeply integrated with the ALU as well. And the cache controls, as I mentioned from the instruction set earlier, these green wires here from the instruction set essentially control if you want to save data to the cache, if you want to read from it, if you want to manipulate it, all that sort of thing. And essentially, the cache is like additional memory, but the key advantage to it is two things rather. One, it is in theory faster than RAM because the cache, the memory literally sits right next to the ALU compared to the memory running down a long bus all the way down at the very physical bottom of the computer, as vertical space is pretty important here. And the second benefit of having a cache is that it is isolated memory. So if you were running multiple cores at the same time and each core needed its individual memory, you would use the cache because each cache is contained within its own core, and you cannot share the data in cache with other cores unless you route it through RAM, because the RAM is the shared memory, and then you could consider the cache as individual core memory. Yeah, and then you won't have to route it through the master output bus and everything like that. Alright, yeah, so since the cache is deeply integrated with the ALU here, it has to be able to basically manipulate data in all ways possible. And a few examples of that are when we have the data sent through from the inputs, you can save it to the cache immediately, and that is on this lane, these buses up here. You can save the inputs to cache, you can save the outputs to cache. So if we see here, there's also another bus that runs vertically here to the outputs of the cache to be able to write to it. And then you can, as with the memory, or not the memory, the RAM, to be more specific, is a dual read as well. So we can read two values at the same time to enable faster computations. And yeah, that's basically it. And one thing is that this memory here is solid state compared to the RAM being, I guess, mechanical. Can I say mechanical? Essentially, the dual read RAM of the not dual read RAM. I'm getting all my terms mixed up. I'm sorry. The dual read cache, the caches in each core don't have any pistons in them. At least the actual physical, I guess each bit of memory. But in the RAM, it does, and that may introduce some instability with high-speed signals, with zero-tick pulses and that kind of thing. But yeah, that is essentially the cache. It was intended to be a very versatile and nice addition to the Redstone computer to enable more efficient programming and processing of data and that sort of thing. So once, let's say, once your computation is complete from the ALU, the data travels down into the master output bus, and let's say you want to go ahead and output it to one of the displays or that kind of thing. So how would that work? So essentially all of the data from all cores comes up to around here, and then it gets split off into the different possible outputs that we can use. So let's see here. I'm pretty sure this is where, right here, or what am I trying to say? There are different outputs, so you can output to the parallel output port, which essentially is like it's a USB port, but it's parallel, which essentially means that you have all 8 signals instead of just one. So here's a parallel output port. You can output your data to that. And then you can connect this to like some sort of other device that you've created, like over here or something. And you can also output it to the decimal display and the raw binary display, and that is through here, I'm pretty sure, these two registers. So the master output bus connects to these two registers, and the right line on these registers is controlled by the opcode that we talked about earlier, which is right up here, the IO output opcode. And then once you've selected the specific display in the options section here, it will basically enable the write on that register to allow the data to go through to that. And we also have the master output bus connecting to the GPU or the plotter, and I will explain this later as well. But this is where the specific coordinate data goes compared to the I guess mass image data, if you will. And that is about it for peripherals and that sort of thing. We also have the parallel input port, which is connected to the master output bus as well, because data that, let's say for example you had a encoder or something, and that would connect to this, like some sort of device, you would want that data to be saved somewhere, and that is how it is done. So once the data is sent through here, you can save that to memory and then manipulate it to your liking. Alright, so now that I have broken down most of the computer, that essentially, a lot of those things that I just described were pretty similar compared to the Redstone Computer 3.0, except the cache, which I described a little earlier. That is new on the Redstone Computer 4.0. But if you've seen the Redstone Computer 3.0 breakdown video, you can see that a lot of the fundamental concepts and the computer model essentially of this computer is pretty similar, in fact, to the Redstone Computer 3.0. It is just more upgraded and it's faster and more efficient and that kind of thing. But now I want to talk about the big elephant in the room here, the most obvious new additions to the computer, and that is the GPU plottered display thing here. And in the Redstone Computer 3.0, I was not able to include a plotter because I essentially didn't have enough space for it and everything. I didn't really plan for it, that kind of thing. But in this computer, I made sure that I was able to get this in, and I did. And I want to explain how this whole thing works. Alright, so to start off, we are going to go ahead and head back to the opcode decoder of each core, or at least for core 1 here as an example. And as I mentioned earlier, we have 4 specific opcodes for controlling the plotter and what is put on the screen. That is GPU reset, GPU draw point, GPU erase point, and GPU granular. So the GPU reset, this is pretty self-explanatory. This just sends a signal to the GPU to clear the screen essentially, and that'll wipe all of the pixel data off of the screen. And then we have the GPU draw point and erase point commands or opcodes. And essentially what this will do is that this will enable a specific coordinate to be sent to the GPU. Since the screen is 15 by 15, every single pixel on here can be encoded into an 8-bit number, which is oh so convenient. It's not like I planned that or anything. But essentially how you send this encoded coordinate to the GPU, it takes a multitude of steps, but we will start off in the RAM here. So let's say you wanted to encode the point 5, 7. So what you would do is that you would read the numbers 5 and 7 from RAM, and then that would propagate up through these buses into the input of the core, or input of the ALU here rather, or just the core in general. And this signal will be sent through to the GPU encoder, which I mentioned I would talk about, and here we are talking about it. So this is the GPU point encoder, and essentially what this does is that since the screen is only 15 by 15, there only can be 15 by 15 amount of pixels. So what it'll do is that it'll take each 8-bit input and split it in half, and take 1/2 from the first input and 1/2 from the second input and combine them into one 8-bit number. So for example, if we had 5, 7, the GPU point encoder would take that 5, which is only encoded in 3 bits out of 4, and it would put that in the first part of a new 8-bit number, and then 7, it would also do the same thing. So now you have those two numbers 5 and 7 in one 8-bit number, which is then, once it's encoded, is sent back to the output of the ALU and saved in the register. And then if you want to draw a certain point or erase a certain point, now that that point is encoded, all you have to do is send it to the GPU. So that encoded point will be sent onto the master output bus, and it would make its way onto this bus right here, where it basically makes its way into the GPU controller, which is back here. And I will go in more depth into that in a minute. And once that encoded point is sent and you have a draw point or erase point command, it will be executed, and then you will see that point essentially appear or disappear on the screen. Alright, so that covers 3 GPU opcodes, but the 4th GPU opcode here that we have is GPU granular. Now this is a pretty data intensive opcode, and that is the only function of, let me see if I can get through here, of this massive 30-bit bus right here that you see that runs into the GPU plotter and all that stuff, and it's connected to all 4 cores, as you can see here. So it is a pretty massive bus, and it carries a massive amount of data, to say the least. Alright, so how does this GPU granular opcode work specifically? Well, you can send specific points of X and Y coordinate data to the GPU all at once, instead of sending it individually one at a time like you would with the draw point and erase point opcodes. So for example, if I wanted to draw an entire line on the GPU at one time, instead of drawing each and every single point on that line, we would be able to use the GPU granular opcode. And the way that works is that you just toggle the opcode here, and then you input your image data in the instruction set in the 30-bit gray bus. So 15 bits are for X and 15 bits are for Y, and that corresponds for each position rather on the X and Y plane for the plotter. And there are some options that you also can select in the options component here, the instruction set, to do a thing called fill X or fill Y, and essentially that is filling certain points of the display. So if you had a point here and a point here, instead of specifying to draw all the points in between in this bus, you could just say fill X, and then it would fill everything in between for you. So that is just a convenient little tool you can use. So that is essentially how the GPU granular opcode works, and that is how the checkerboard program is able to run so quickly. In just 2 lines of code, you have exactly half of the screen. It's like 128 bits or 8 bytes of image data sent to the screen in just 2 cycles, which is pretty crazy, because if you were to do that with the GPU and erase point and GPU drop point, if you were to do it one at a time, it would take significantly longer, and you wouldn't have, I wouldn't think you'd have enough space on one core to execute that operation. So that just shows the power of the GPU granular system that is included in the Redstone Computer 4.0. Alright, so now that I have explained the GPU operations and how to control the GPU and everything, let's go ahead and take a look at the controller behind this thing. So, if we look back here, this is essentially the same controller, or the same plotter VRAM video memory that the Redstone Computer 3.0 has, except I have modified it and added some things to it. And this originally is Bennycube's design, so I want to give him credit for that. I think he makes an amazing design here, and that's why I've decided to use it. So let's begin down here. So the data for the specific encoded points is here, and it runs down and it splits up here into decoders. And these lines of 4 bits each, because remember, there's only you only can have 0 through 15, so that's 4-bit numbers. So those 2 encoded 4-bit numbers get split up, and then it runs through these decoders here, and essentially this selects one X position and one Y position to select on the screen. And then once that happens, and then that actually runs through up here. So let's see here. The Y data, like see which row to write to, is controlled by these wires here, and then the X data runs through here, and then this runs into the back of the memory and into the memory itself. So this is basically a bunch of D flip-flops essentially in here. So it's super compact and I love it. And let's see here. So that data runs into there, and then we have our 4 opcodes right here, the GPU opcodes. So we have GPU reset, that runs up into here, and this essentially clears all of the memory. So this is, essentially sets or writes zeros to every single position in the screen. And then we have GPU drop point, and that draws a specific point on the screen, and that runs into the controller. And then we have erase point, and that also runs into the VRAM here. And I had to modify Bennycube's original VRAM design here to include a singular erase point option. But I thought that would be necessary so that we could have a functional plotter here. And then the GPU granular opcode essentially runs down here and enables the different options I was talking about with the fill X and the fill Y, and it opens all of that up. So it basically allows all of these signals to run through into the VRAM as well. And since we're here, I'll explain how the fill X and the fill Y work. So essentially, if you have 2 coordinates, so let's say you had a coordinate here and you had a coordinate there, and you wanted to fill everything in between. When you selected the fill X or the fill Y, it would literally, if you see here, there's repeaters that are basically chained all the way down, and it will essentially power every single input in between those 2. And that is how that works. And then all of that data is sent up here to be updated with the screens that can be shown on the display. So that is essentially how the controller works and how the data is processed for the GPU. And yeah. Another thing that is different between the Redstone Computer 3.0 and the Redstone Computer 4.0 is that, pretty obviously, as you can see here, this has a lot more program memory compared to the Redstone Computer 3.0. In the Redstone Computer 3.0, there were 20 bytes, not 20 bytes, excuse me, 20 lines of code that were in the Redstone Computer 3.0 with a hardware maximum of 31 lines of code. And for the Redstone Computer 4.0 here, excuse me, there are 64 lines of code rather, 64 or 63. I'm pretty sure it's 63, but 63 lines of code. So that essentially triples the lines of code from the Redstone Computer 3.0 to the 4.0. So you can have much larger programs on the Redstone Computer 4.0 compared to the 3.0. And also another difference in the instruction set for the Redstone Computer 4.0 compared to the Redstone Computer 3.0 is the fact that the Redstone Computer 4.0 has the ability to change the speed of its own core through the program instead of through the user input panel here. So as you can see, we have 4 bits of orange space here, and essentially if you want to change the speed of the core, so let's say you anticipated operations where the computer can run faster and execute those instructions faster, you can change the speed in advance to speed up the computer to allow faster execution of those lines of code. And then let's say you started, you knew you were approaching more core or computer intensive instructions such as drawing to the GPU or doing ALU calculations, you can slow down the computer in advance, the core specifically, so that everything stays stable and that sort of thing. Alrighty, so that is basically the entirety of the Redstone Computer 4.0 broken down, and hopefully by the end of the video here you guys now know at least a little better than you did before how the computer works, how things are managed, how the data flows through the computer, how this GPU works or the plotter, how their cache works, how all of this mass of redstone comes together to make what I call a redstone computer. So yeah, thank you guys for watching, and thank you guys for the immense amount of support that I have received throughout these past several months. I know I say it all the time, but I've been super busy, and I haven't been able to put videos out, but I'm going to start putting more videos out hopefully soon. I have a lot of projects I'm working on, a lot of ideas. So I just want to thank you guys for your immense amount of support throughout this time. And yeah, thank you guys so much. I will see you guys in the next video. And yeah, peace guys.